Equation RL and RLC. I will take that to module number 5 because here it becomes an island. It may create some confusion to all of you. So now with this I hand over this presentation to Professor Somnath Gupta, and he will brief you about some of the analysis, like what is the percentage error and all that, etc., etc. I have done a very crude way, with the assumption that you will be able to do that by some kind of a little effort, but he will give you some more input. So it's over to Professor Gupta. Let us start now because I think one third students, more than one third are there. If I'm not wrong. We can start our talk now. Professor Gupta, now you
Yes,
can take over.
it's a good evening, sir. Am I audible?
Yeah, I can hear you. Students also should hear you.
Okay, sir. Yeah, this is basically some related to some tutorial topics that will be helpful for your exam also. Okay, so whatever Patak sir has discussed in last class, it is the extension of some points on and it will be basically finding some parameters. Okay, so we'll see it. So now it is 5 minutes over, so we can start now.
Yeah, of course. There is no point in wasting time. You should feel comfortable. You take your own time. Nothing like very hard limit that is exactly at 10 minutes it should be over or so. You take your time comfortably. Don't worry.
Okay, sir.
Put your video also is better. Students can see you that way. Speaker should also be visible to the audience.
My video.
Yeah,
Actually,
if possible. If it's possible, otherwise no problem.
it is actually it reduces the bandwidth.
Yes, sir.
Yes, can.
Okay. So we have seen that for we are discussing the response of RC circuit for different types of inputs. So one such input was square wave. Okay, so you know that uh, there are some properties of RC circuit like it does not allow the DC signal to pass. Basically, if it is high pass RC circuit, it does not allow the DC signal to pass. So it blocks the DC signal. And suppose one square wave input is there and it is clamped to a certain DC level. So at the output, what we see, the DC level is removed. So the top figure is basically one square wave input, and the bottom figure is the output of that RC circuit, a high pass RC circuit. And another thing to notice that if there is change in the uh, input voltage, there is some instantaneous change or sudden change in the input voltage by some amount, then at the output also there will be that much amount of change. So if say this side, if the input voltage changes by this amount from V dash to V double dash by amount V, let us say, so at the output also the same change will occur. Okay. So there are certain points basically written over the slides that average level of the output signal is always 0 for high pass RC circuit, And when the input changes discontinuously by amount V, the output changes discontinuously by an equal amount and in the same direction. And when the input maintains constant level, the output decays exponentially towards zero. So what is the meaning of that? That this it blocks the DC signal, and if there is sudden change in the input, output will also be changed by that amount. And if the input is staying at constant level, due to we take the output across resistance, so there will be decay. It decays towards zero. So these are the three main concepts. Now, uh, and depending on the conditions for RC, that is value of time constant, the wave shape will change. Okay, so uh, if the value of time constant RC is large, that time it almost say it is very large, so it almost resembles to square wave or the input applied. But if the time constant is small compared to the time width, the pulse width, then there is the wave shape will change. Okay, so let us see what kind of wave shapes is produced. So we have considered this waveform. So this dotted one is the input signal, that is square wave, and the bold line is the output signal. Okay, so what will be the parameters that I told that for at the output signals? So we consider one square wave of on time period is say T1 and off time period is say T2, although it is maintaining certain voltage level at V1, okay, for time duration T1 and V2 at time duration T2, and they change by an amount V. Okay, when that is the input. So this is the input from this dashed line. Okay, now V1 dashed is the voltage. Okay, at time t is equal to T1, and V1 is the is your say in this is the steady state waveform at the output. So initially say at time t is equal to 0, although it is steady state, but for analysis purpose we say that it starts from t is equal to 0. Okay. So at t is equal to 0, this voltage, initial voltage at the output is V1. Okay. Then due to decay of the waveform, since we are taking across resistance, it will be having this relation V1 dash is equal to V1 into e to the power minus t by RC. So at t is equal to T1, it is V1 into e to the power minus T1 by RC. This is one equation. Another equation is V1 dash minus V2. Okay, this V1 dash minus V2 would be equal to V. Okay, that is the change in the input, sudden change in the input V. So that will be reflected in the output, okay, by same amount. So that is V1 dash minus V2. Okay. Then from V2, this is the voltage at T is equal to T1. Now there will again decay because input maintains constant level, as it was discussed that input maintained constant level, there will be decay in the output across RC. So this decay would be accordingly V into e to the power minus T by RC. Okay, so that means initial voltage is V2. Okay, and at this point V2 dash is equal to V2 into e to the power T minus, because now it is delayed, so by T1 amount. Okay, if you consider the origin at T is equal to 0, so this value will be delayed by T minus T1, so that it starts from here, T is equal to T1 and by RC. So this is the value of V2 dash. Okay, then but since uh, we consider t is so this value is what is actually this duration is t2. Okay, this duration is t2. So this is actually time uh, t is equal to t1 plus t2. This v2 dash is actually t1 plus t2. This is t1 and this is t2. So this in place of t, we write t1 plus t2. So t1 will cancel out. You will get v2 dash is equal to v2 into to the power minus t2 by rc. Okay. So again, there is change in the input voltage V amount. So output will also be changed by that amount. That is V1 dash minus V2, V1 minus V2 dash is equal to V. So these are the four equations, 1, 2, 3, 4. So these four equations will be used to calculate the percentage of tilt. Okay, see tilt because this you see that the square wave is getting tilted due to the response of this time constant, okay, which is slightly high, okay, RC. So this it is wave shape does not remain same. Okay, so this so now what we see that now we consider one symmetrical square wave case, okay, where the voltage levels, that means in positive and negative sides, are same. So in positive side it is plus V, and another negative side it is minus V, and also the duty cycle is 50%. Okay? That means T1 is equal to T2 is equal to T by 2. Okay? That is the time period of the square wave. T1 is equal to T2, that is T by 2. That is these time durations are same. On time and off time duration are same. In that case, what happens? V1 is equal to minus V2. So this is V1 and this is V2. These two voltage will be equal and opposite. So let us say instead of keeping V, let us keep it the same one, that is V1. So this V2 would be equal to the minus V1. Okay, say this is plus 2. This will be minus 2 volt. Okay, then V1 is equal to minus V2, and V1 dash is equal to minus V2 dash. So that means other this voltage, lower voltage, V1 dash is equal to minus V2 dash. That is equal and opposite. Then so using from these equations, the previous four equations, okay, you can write that V1 dash is equal to V1 into e to the power minus T by 2 RC. Okay, so that means in place of T1 we write T by 2. Okay, that is capital T by 2 is half of the time period, so it becomes minus T by 2 RC. Okay, then V2 dash is what? V2 dash is V2 into similarly minus 1, T2 is equal to T by 2, so it is T by 2 RC. Okay, T by 2 RC, V1 dash and V2 dash. Now, since V1 dash minus V2 is equal to V, that means V1 dash minus V2, this equation is V. So we can write V1 dash is equal to V plus V2. Okay, or since V2 is equal to minus V1, so you can write V minus V1. So this V minus V1 is actually what? It is V1 dash. Okay, so this V1 dash is what? V1 into t to the power minus T by 2 RC. So this V minus V1 is actually equal to V1 into t to the power minus T by 2 RC. Okay, so now this again uh, so from here V minus V1 should take V1 right side, so it becomes V is equal to V1 into 1 plus e to the power minus T by 2 RC. So this V1 is equal to V by 1 plus e to the power minus T by 2 RC. Now here we have got one series, okay, that is in the form of uh, uh, this e to the power minus t by 2 rc. It is written as 1 minus t by 2 rc plus t by 2 rc whole square factorial 2. So this is the formula for e to the power minus x. You may be knowing it well. So this terms t by rc or t by 2 rc, what we have assumed, the time constant rc is large. Okay, so t by rc terms will be small, and even the higher order will also be small. That is, so we can ignore the higher order terms, that is t by 2 rc whole square, t by 2 rc cube. Like those terms will be vanished. Now it will become v by 2 minus t by 2 rc. So it is v by 2 into 1 by 1 minus t by 4 rc. Okay. So, and 1 by 1 minus x can be approximated to 1 plus t by 4 rc. Okay. So this level V1, voltage level V1, okay, that is this value V1 is uh, now coming to be V by 2 into 1 plus T by 4 RC. Okay. So again, uh, uh, the other values, that is lower one, okay, V1 dash would be what? That is V minus V1, okay, V minus V1 as we found. So in place of the V1, we write the value, that is v by 2 into 1 plus t by 4 rc. So it becomes v by 2 into 1 minus t by 4 rc. So what we have calculated, this voltage level v1 and that this voltage level v1 dash. Okay, that is starting and ending, these two value within a part of the square wave, within half cycle of the square wave, starting and ending value. So uh, so what so uh, mm, so these are the two final equations of these two voltage level v1 and v1 dash for what? Large time constant rc is high. Okay, t by rc is low, that is less than 1, but same thing, rc by t is high. Okay, that is very much greater than 1. So now the parameter, that is percentage of tilt for a square wave. So what is the meaning of it? How much it will tilt depending on the frequency, depending on the time constant, how much change or bend will be there in the square wave. So this is P is equal to V1 minus V1 dash, that is initial and final values within a half cycle, V1 minus V1 dash divided by the average level, okay, V by 2, okay, V by 2 into 100. So it is putting those all values, we get T by 2 RC into 100%. Okay. Now the cutoff frequency is 1 by 2 pi RC or lower 3 dB frequency for RC circuit. So we can correlate that this P is equal to pi into F1 by F into 100%. So if you know the input frequency, and know the time constant, input frequency F and time constant RC, or probably the cutoff frequency F1, then you can find the percentage of tilt in the square wave. Okay, so this thing I wanted to explain. Uh, so there are some other few topics also. So anything up to this uh, you want to discuss? Anything up to this, or is it clear?
Clear,
Okay.
sir.
Any question? Any question? Harshvardhan?
No, sir. Clear, sir.
Okay, fine. So we move to the next input, that is ramp input. Okay. So uh, ramp input is basically a linear waveform which is given by V is equal to alpha t. Okay, it is a straight line equation. Alpha is the slope. V is equal to alpha t. Okay. So let us see what is the input output relation, that is basically differential term would be there. So in this circuit, Vi is equal to what? The voltage across, if you apply KVL, then it is voltage across capacitor and voltage across resistance, that is V naught. Okay. So this Vi is equal to the current you see that capacitor voltage is how much? Charge by capacitance. So it is Q by C, charge by capacitance, plus V naught. So now if you differentiate this, okay, dvi dt, so it becomes IC into 1 by C into dq dt plus dv naught dt. Okay. So this this dq by dt is what? It is the current, okay, rate of change of charge carriers. So I by C plus dv naught dt. Okay. So this I by C is what? I is equal to what? Can anybody tell? I is what? What is the value of I in this circuit? Let us say I is flowing through the circuit. Okay. I is flowing through the circuit. So it is V0 by R is the current I, okay, through the circuit. If you know the voltage across resistance, okay, if you use this variable output voltage variable across R, okay, then the current would be voltage by resistance, so it is V0 by R. Okay, so in place of I, we write V0 by R divided by C into plus dv naught dt. Okay, so this is the input output relation. Okay, the differential equation, that is time domain equation, not in Laplace domain. Okay, time domain equation of input and output. Now this dvi dt, again I have rewritten here. Okay, dvi dt is equal to v0 plus v0 by rc plus dv dt. So this dvi dt is what? This vi is equal to alpha t. So dv dt is equal to alpha. Okay, so this alpha is equal to v0 by rc plus dv dt. Okay, so this is the uh, uh, this is the your output relation of or equations for output waveform. Okay, when ramp input is applied, so it is a differential equation. Okay, so you know that when initial voltage is t is equal to 0, so using some initial condition, you can find, applying some initial condition, you can find the solution of this differential equation. Okay, but we can use other method like Laplace transform to find the output waveform. Let us say, so that is, but this is required, okay, for understanding the behavior of the circuit. Now again we want to do for using Laplace transform the same, the solution of v0t output equation v0t using Laplace transform. So what we do, again we apply Laplace transform on this equation. Okay, so alpha is there, so Laplace transform is will be alpha by s, since it is a constant, and since it is v0, so it is v0 by r, v0 s by rc, and since it is differentiation dv0 dt, so it will be s v0 s minus v0 s. That is the initial value of the output voltage. Okay, t is equal to 0. So v0s by rc is equal to s plus v0s, because initial voltage would be 0 at t is equal to 0, because it is a ramp signal, it starts from t is equal to 0. Okay, so plus sb s0 is there, so we get v0s is equal to 1 by rc plus s, so it is alpha by s. So this v0s is equal to alpha by s into s plus 1 by rc. Okay, this is the Laplace transform of output equation. Okay, now if you next what we see now, just slightly arranging these terms, okay, like we do in partial fraction form. So we have divided into two terms, src into 1 by s minus 1 by s plus 1 by rc. So again, what we do, we apply inverse Laplace transform, so it becomes alpha rc into 1 minus e to the power minus t by rc. So again, writing the series of e to the power minus t by rc, and this, okay, t by 1 will cancel, so it is t by rc minus t square by r square plus dot higher order terms. So we take alpha t rc into this equation, so it becomes alpha t minus t by rc plus the other terms. So this is the output equations when ramp input is applied. Okay. Now, uh, now there are some parameters like transmission error. Okay, these are there. So what is the error? Is actually vi minus v0. Okay. So actually, what happens that when you apply ramp signal, it deviates. Okay, deviates from the input ramp signal, and later it become constant. Okay, because it is a differentiator. RC circuit is differentiator. Okay, so if you differentiate the straight line, okay, it will become constant. We differentiate a straight line, okay, alpha t, so it will become constant. So this, that's why it will deviate after some time, it will deviate. Okay, so so departure, so there will be departure from linearity, and let us define transmission error is the et as the difference between input and output divided by the input. So we divide difference, calculate the difference vi minus v0 divided by vi, so this is alpha t into this one. Okay, so finally we get that it is coming to be t by 2 rc, depending on if rc is high. Okay, if rc time constant is high, then this it will uh, deviate from linearity. Okay, and it can be related to the this uh, this this f1, that is cutoff frequency. Okay, now uh, if t by rc is small, okay, then this term, if t by rc is small, it is very important conditions that if t by rc is small, this exponential term will be very small, so it becomes alpha rc. So it becomes alpha rc. Okay, only this one alpha rc if time constant is small. But if time constant is large, okay, there is some deviation. Okay, so for both conditions, like rc is small, rc is large, there are deviation is small in case of rc is large, and deviation is large in case of RC small. So that is the concept, and sometimes it is used for measurement of slope, okay, of a sweep circuit. Okay, so now another exponential input. I have given some notes from the book. Okay, you just go through it for exponential input, and uh, if you have any doubt, you can ask. Now we'll go to the low pass RC circuit. Okay. I just want to give some basic uh, formula based on Laplace transform. So nothing else here I want to put. So what is low pass? What is low pass RC circuit? Is that uh, it is if you take across voltage across capacitance, okay, then it will be low pass RC circuit, and that passes low frequency. Okay, so but because for high frequency the capacitor will be short circuited, okay, and output will be zero. So but if for low frequency it remains open, so you will get the input voltage past whatever it is coming at the output. Okay, now what is the input output relation? The way that we earlier have seen, that using Laplace transform we finally get V0 by Vi is equal to 1 by 1 plus SRC. Okay, so here again there is cutoff frequency 1 by 2 pi RC. Okay, and at that cutoff frequency we get 3 dB loss. Okay. So there is some phase relation. What is the phase? That is minus tan inverse omega RC. Okay. Now first case we consider that step voltage input. Now what is the formula for step voltage input? So as the relation is V0 by Vi is 1 plus 1 by 1 plus SRC. So it is in place of VIS, okay, we write differential for step voltage it is Laplace transform is V by S. So we just write V by S here. Okay, in place of V by S in VIS we write V in V by S. So it is V by RC into this one. So finally we get output voltage VOT is equal to V into 1 minus, it is equal minus T by RC. Okay, so actually I have not drawn the waveform here because I could not get time. So because what happens in low pass RC circuit, the capacitor charges to the applied input voltage. Okay, so it is an increasing function for low pass RC circuit. The output voltage is an increasing function, and for high pass RC circuit it is a decaying function. So this thing you have to keep in mind. So this increasing function, okay, so it is you see it is 1 minus some decaying function, so that means it is increasing. So if you have any doubt you can ask me now, and I will hand over to Professor Pathak if he wants to tell some other topics today. Okay, or if you have any doubt you can ask me. Yes, students, please.
Okay, so friends, question is coming. Yes, question. A question was coming. I stopped.
Are you listening? What is told today?
Yes, sir.
Okay, so Professor Sen Gupta has attempted the analysis work with some kind of formula for quantitative calculation of those values. Yes. And you must have seen what trick is applied in that quantitative analysis is the exponential rise and exponential decay that is approximated by straight line, ramp or slope. It's not exponential decay and those numericals are solved. Why it is so? Because the deviation from one value to the other value when it is false, it is very small. Within that range, you can approximate it as a straight line. So it is a, you can say, linear slope, and that's how it has been solved. Okay, so even square wave if you are taking, it is falling to say linear slope from one peak value to some intermediate value, then sudden jump, then again it is rising. Rising is approximated by a straight line because the very narrow range in which it is going. Just you can see that here the diagram is there. So that is approximation. It is well taken. It is valid also. So you are also free to use the similar approximation rather than getting involved or locked in your exponential kind of calculations. Is that okay? So here given a very nice view of the topic that you have done so far, and we are at the end of your module number 1. So I think you should have all your questions when it comes to your mind. So you want any kind of your summarization? It's okay, understood for you. You see, it is like that. Only three things we are doing for both the circuits. One is your CR circuit, high pass circuit. When the input is sinusoidal, okay, input voltage is sinusoidal, what is your output voltage? Output voltage is appearing across the resistance. So sinusoidal input appearing across the resistance, that is your V naught. And you calculate for input as sinusoidal, input as a step voltage, what is going to be that output? The final output will become 0 if it is step input. Why? Because the capacitor is coming in series, it will block the DC value. And then step voltage, what is the DC value? The voltage itself is the DC value, so it will be totally blocked. So output at the final stage, it will become your 0. Initial stage, whatever input was given, it appeared at the capacitor's output, so V naught was equal to your applied step voltage. So from there, it started falling to the 0 value. So that's what was the output coming for the step voltage. And for the ramp, if you are coming, you are having input voltage minus the voltage across the capacitor, that is your VC, that is becoming your V naught. So you are solving for V naught, it becomes your first order differential equation. Okay? And there, if you put the value of the input as your ramp equal to alpha into T, so d dt of alpha T becomes your alpha. But d dt of V naught will not be your alpha, will be something else. And that's how the ramp will be calculated for high pass circuit. Okay. For low pass circuit, your output is taken across the capacitor, and that's how the values will change. Here the final value will not be 0. Okay. So because the capacitor will keep on charging like that. So I think these things you work out, maybe in the next class on Monday, I will try to summarize this thing. If you are going from high pass to low pass, same thing, step voltage input to low pass circuit, how does it affect? If it is exponential, how does it affect? If it is going to be a ramp, how does it affect? A square wave, I have already explained. There, the decay was shown as a linear slope, not as an exponential decay, because the fluctuation range of the voltage was very small. And that's why you can approximate by some kind of straight line using the first order approximation. Is that okay? You want me to go for any detail today, or you prefer to wait for Monday? What is the opinion? Still time is there, 15 minutes are there. Okay, anyway, let me put something, because I said we are coming to the end of our uh, module number 1. After 5 lectures, normally module 1 is completed. RL circuit and RLC circuit I will be taking in module number 5, when sweep generation will be taught. Current sweep, voltage sweep, those generations will be using inductors also. Sometimes I'll talk over there. Okay, for the switch as such, inductor is not of any much use or something like that. Okay, so I take the board now. The handler. Yeah, these are thing I said. Okay, fine. One circuit was like this, high pass circuit, and we are going for the output like that. This is my V naught, this is my VI. In whatever way I am putting now, VI function of t, V naught coming as a function of t. Then another circuit was described when this was the resistance, here was the capacitance, and this was my voltage V naught t, and here is my VIT. Sinusoidal case, Professor Gupta has explained very detailed manner, so I am not going for that. VIT is some sine wave, V naught t will also be a sine wave, but it will be constrained according to the frequencies. In both the cases, one becomes high pass, one becomes a low pass, that way. So first one was that he explained was sinusoidal input. बंद मत करिएगा आप लोग. Sinusoidal input, okay? That you have seen, high pass, low pass, 3 dB cutoff and all that is coming. Whatever the phase is changing, that is also described as arc tan inverse of imaginary part by real part, and that way you got it. Now second thing it was described was your step voltage. Input was step voltage. If I am applying step voltage to this one, what is going to happen? Voltage immediately appears there, but that will become zero because capacitor initially it is not charged, so it will be grounded. So V naught here, for the step voltage, it will be your zero at this point. Now voltage is a step voltage, capacitor keeps on charging through this resistance, and as a result, it increases something like that. Okay, it becomes like this, step voltage, it becomes like this. So in this case, when the step input is there, this is my V naught. What is that? It is your V into 1 minus e to the power minus t by RC. What does it mean? At t equal to 0, the voltage is 0, V naught is 0. At t equal to infinity, this voltage becomes your V. So this is going to be my V naught t. Okay? In this case, what happens? It is different thing. Step voltage I applied. I apply the step voltage here. Voltage appears here immediately. This becomes my V naught. Okay? So to solve this equation, we put like that as your V naught t equal to let us say B1 plus B2. These are constants, e to the power minus T by RC. That's how it will be charging according to this T. What is B1 and what is B2, that we have to evaluate here. Here it was not needed, remember. But here I'll be needing this B1 and B2. What happens when T becomes infinity? T becomes V naught, becomes a V naught final, V naught F. That will be what? This becomes your 0, that is your B1. So T equal to infinity, it becomes your V naught F. Okay? And I'll come to that. What is the value of V naught F? What happens at T equal to 0? Another limit will come. My V naught will be initial value. Initial V naught. Okay? And that will be given by B1 plus B2. Okay? So B1 is your V in the final voltage. B1 plus B2 is the initial one. So what is your B2 now? Your B2 comes out to be here. I'm talking of a step here, okay? Not the ramp. B2 will be V initial voltage minus B1. B1 is your V final, what is that? VOF rather. VOF. That is my B2. So equation becomes my V naught T. That output he has explained in a very nice way. I'm putting that in this form. B1 is your VF, VOF rather, VOF bracket, it will be 1 minus is it there? Okay, let me see. What is the V initial value of V in? V init at output, what is the initial value here? Whatever voltage applied, the step has appeared at this. So V init becomes your V. This becomes your V. I'm writing a phrase here. 1 second, it is coming here. Okay? So V naught T I want to write is your B1, that is your VOF. VOF final, it is 0. Because this is blocking the DC. Capacitor will block the DC. And the total voltage DC. So my VOF becomes my 0 plus B1. What is my B1? Sorry, B2. So what is my B2? V initial at the output minus VOF. V initial output is what? Whatever voltage, step voltage I applied, minus 0. E to the power minus T by RC. That's what I have assumed, B1 plus B2 into T e to the power minus T by RC. So it is nothing but V into e to the power minus T by RC. When T equal to 0, it is V. So initially it is V. When T becomes infinite, output becomes 0. So this V naught T is for the high pass case, this for the low pass case. Understood now? Same thing happens for the step voltage. I think time is there for the step voltage also I can take up. 2 minutes are there. No, that 10 minutes are over. What do you think? Should I take a step voltage also here itself?
No, sir.
No, okay, fine. So on Monday I will summarize that. And Monday it will be the discussion hour. Maybe I'll take some example to solve it. So I'll say that yes, after 6 lectures we are completing the module number 1. Okay. and module 2 maybe you will be starting on Monday itself. So after that, the quiz for module number 1 will be decided. Okay? So we summarize here. Thank you, Professor Sen Gupta, for the input that you have given
It's
to the
my pleasure.
students. I just I appreciate that. We can do it at some intermediate stage also like that for the convenience of the students. Thank
Yes,
you
sir.
very much. So I'll see you again. There is no question? Quick question? Oh, okay, fine. Come prepared with your questions.